Hey guys, about to start doing some Lewis dot structures. I think this is the fourth video in chapter 8, maybe. So we're going to do two molecules to start with that electronically seem like they should be very similar to each other, but as we get into it, we'll start to notice some differences between them. So the two molecules, we have SO2, sulfur dioxide, and we have ozone. So first of all, you might think, why are these two molecules similar? Like one of them, O3 is three of the same atom, but yet SO2, there's different atoms involved. Why would they be similar? Well, basically for each one of these, there has to be a center atom and then two on the outside. So for SO2, how do I know which one's in the middle? Again, the first rule that I go by is when I think about how many bonds each atom needs, the one that needs the most bonds is always going to be in the middle. Okay? So sulfur is in group 6 of the periodic table. That means it needs to make 2 bonds to get an octet. Oxygen is also in group 6, so it needs 2 bonds to get an octet. So at that point, if the sulfur and the oxygen both need 2 bonds, then my first rule doesn't work because they need the same number of bonds, so I can't choose between them. So my fallback to that is, if you have 2 elements that want the same number of bonds, the one that goes in the center is going to be the one that is less electronegative. Okay? And actually that really in most cases probably is the primary thing to look at, but I don't know, the thing about the bonds works 99% of the time. So SO2, the electronegativity does decrease as you go down and to the right of to the left of the periodic table. Sulfur is further down than oxygen, so it's less electronegative. That's the one that goes in the middle. So I'm going to put S with the 2 oxygens around it. Then I say, okay, the outer atoms are always going to get their octets. I don't have any charges in SO2, or at least I don't have an excess charge to deal with. So that means that the 2 oxygens are going to have to get to their octet in a normal way. If they have 6 dots, that means they're going to need 2 bonds. So I'm going to make a double bond between this oxygen and sulfur, and then I know that to get 6 dots, 1, 2 in the bonds, 3, 4, 5, 6. That's a normal appearance for oxygen. The other oxygen's gonna have to do the same thing, make a double bond to the sulfur, and then make my 2 lone pairs on the oxygen. Okay? Both of my oxygen atoms have now their octet. Sulfur really only wanted to make 2 bonds here. If he makes 4 bonds, that's more than he wanted to make to get an octet, so that means that he's gonna exceed the octet. If you make more bonds than you want, you're gonna go beyond the octet rule. Okay, so how many does it end up with? Well, sulfur is supposed to have 6 dots around it. Right now, I've already used 1, 2, 3, 4 just to make the bonds. That means there's 2 left over. And leftover electrons are always going to pair up. So the sulfur is going to have a total of 4 bonds and 2 electrons left over. Okay, that's 1 lone pair. Now, when I look at that and say, okay, sulfur exceeded the octet, by how much did it exceed the octet? Well, if I count how many electrons it owns, 1, 2, 3, 4, 5, 6, those are the electrons that I would look at if I were trying to determine the charge of the sulfur. This sulfur atom has 6 electrons around it, so it does not have a charge. But then I'm looking at how many electrons is it involved with, either that it owns or is sharing. Then I have to count the ones on the other side of the bond. Sulfur owns 1, 2, 3, 4, 5, 6, but it's sharing 7, 8, 9, 10. The electrons from the oxygens are also being shared with sulfur, so this sulfur atom has access to 10 electrons. That's more than 8, which is why we're saying that it exceeds the octet. Okay, so that is the structure of SO2. Sulfur is allowed to exceed the octet. We said in the last video, only elements that are in the 3rd row and below can exceed the octet rule because they have, in the 3rd shell, you have 3s, 3p, and 3d orbitals. With all those orbitals, you can put more than 8 electrons in. Okay, so that's my Lewis dot structure for SO2. Now, let me separate off. Now we're going to look at ozone. Ozone is O3. Again, one of the oxygens has to be in the middle. So I put one in the middle, put the other 2 around it. if I apply the same logic that I did over here, again, the outer atoms both want 2 bonds each. The middle atom only wants 2 bonds. The outer atoms are always going to get what they want. So I go ahead and say, well, let's just stick all the double bonds on there. Then I have to fill out the lone pairs. So my outer atoms have 6 dots each. When they make 2 bonds each, that gets both of them their octets. But then the center atom, he's supposed to have 6 dots also. I've used 4 in the bonding, so I put the 2 above it as a lone pair, which they could be below, it doesn't really matter. But that oxygen atom in the middle has now exceeded the octet. He has 10 electrons around him, and we just said a minute ago, sulfur is allowed to exceed the octet because he's in the 3rd row. Oxygen's only in the 2nd row. In the 2nd row, that means that the valence shell is the 2nd shell. In the 2nd shell, there's only the 2s orbital and then the 2p orbitals, which is a set of 3. So with 1 2s orbital and 3 2p orbitals, that's only 4 orbitals total, which means you can only have 8 electrons. Oxygen cannot exceed the octet rule. So this structure is not okay. We cannot leave this as our final answer. Okay? It is impossible for oxygen to have 2 double bonds on double bond on each side of it. So what I have to do, I need to take away 2 electrons from the center atom. How do I do that? Well, it's actually really simple. I'm going to take one of these double bonds. I'm going to take one of the bonds from this double bond and I'm going to erase it. So instead of being a double bond, I'm going to erase and make it a single bond. Now when I do that, I just took 2 electrons away. I can't just get rid of them. I have to put them somewhere. Well, if you remember, we said the oxygen in the middle had too many electrons. So when I erase those 2 electrons, I'm going to move them out on the outer atom. I'm going to make them a lone pair right here. So I took the 2nd bond here, I erased it, took those 2 electrons and moved it to the outer atom and said, let's just leave them out here as a lone pair. Now, my oxygen in the middle, if I count up its electrons, it's not exceeding octet rule anymore. It's involved with 1, 2, 3, 4, 5, 6, 7, 8. It's involved with 8 electrons, so it now meets the octet rule. But now I need to think about, it meets the octet rule, but now does it have a charge? Those are 2 different things. It does have a charge because a minute ago it had the 6 electrons it was supposed to have around it. I just took electrons away. So now it's going to have fewer than 6 electrons. Let's count. It has 1 electron that it put in this bond, 2 and 3 that it put over here in those bonds, 4, 5. So 1, 2, 3, 4, 5. This oxygen only owns 5 electrons, so it has a positive charge. It lost an electron when I moved that double bond out here. Now, if he lost an electron, there are 2 electrons here that I moved out. That means that the electron that was here that belonged to him, and we moved it out to this guy, he's going to end up with a negative charge. Let's confirm it. If I count 1, 2, 3, 4, 5, 6, 7 in the bond, this guy owns 7 electrons and then he gains 1 through the sharing, so he has an extra electron. That's a negative. Now, if I add up all the charges in the molecule, ozone is a neutral molecule, so the charges have to add up to 0. No charge here, +1, -1. They do still add up to 0. So basically, I still have all the electrons present that I'm supposed to, but I did have to shift them around a little bit. Sometimes that happens. There's nothing you can do about it. It's just the way it is. Now, is this the only structure we could have drawn? The answer is no. We could have done something a little different. What if, when I had my structure with 2 double bonds, what if I pulled a bond out on this side? Would that have been wrong? So let's draw it. If I have my middle oxygen, and the double bond here, I pull one out, so now this one's a single bond, and this one's a double bond. I'm going to put all my electrons in. So that's the same arrangement as basically just flip the two sides on each other. My middle oxygen still has a positive charge, and the one on the left now has a negative charge. Which of these two structures is more correct? And the answer is, they're both right. Or I could say, neither one's right. Because these two structures, while they're both valid, we're going to call these resonance structures. So let me write the word resonance structures. Basically what happens is neither one of these structures is right by itself. Okay? If I ask you to draw the Lewis-Dot structure of ozone, this is a correct answer. If you, instead of drawing this one, draw that, it's okay too. But really, neither one is completely correct on its own without both being present. Because what happens is, the lone pairs over here, one of these lone pairs at some point might move down in between the two atoms and become a bond, which turns a single bond into a double bond. But when that happens, remember we said oxygen can't be part of 4 bonds? If a lone pair here moves down here, then that means this double bond's got to jump out and be a lone pair out there. And what really happens is the electrons are going to resonate back and forth between, if this one donates down and makes a double bond, then that one folds out and makes a lone pair, but then that one can fold back down and push that one back out. It goes back and forth, which if something resonates, that means switching back and forth between two things. Okay? So the true structure is not this structure, it's not this structure either, it's actually a combination of the two. And electrons move really fast, so actually in real life, we can't distinguish these two molecules from each other. They're the same. And the molecule is going back and forth between them so fast that really the true molecule is an average of these two. So let's draw what would the average look like. Well, my middle oxygen still going to be there. My 2 oxygens on the outside. If I focus on the left side of the molecule, in this structure I have a double bond between these atoms. But if I come over here, in this structure I only have a single bond, which means that between these 2 oxygens, half the time it's a double bond, half the time it's a single bond. So the true form of the molecule is going to be halfway between a single and double bond. So I'm going to draw a solid line and then a dotted line to represent 1.5 bonds. It's a full bond and then a partial bond to show that there's 1.5 bonds between those 2 oxygens. Over here, the oxygen to the right, again, it's a double bond in one form, it's a single bond in the other form. Halfway between is going to be 1.5 bonds. Okay? So actually between the oxygens in the middle and the outside, it's 1.5 bonds on both sides. It's not really a single and a double, or a double and a single. It's 1.5 on each side, and they're actually kind of equal to each other. There's no difference between one oxygen and the other. Up here it looks like one of them has a double bond and one of them has a single bond, but that's not true. It's really 1.5 bonds on each side. Now, we actually know this in your reading about bonding, and I don't even know if it's in chapter 8 or chapter 9, we can determine whether bonds are single bonds, double bonds, or triple bonds by how long the bonds are, like how far it is between the 2 atoms. Single bonds are long. Okay? So imagine if I'm going to give somebody a handshake, that's a single bond between the 2 of us. This works better in class when I have other people here. But in a handshake, I can stay pretty far away from the other person. That's a single bond. If I want to make a double bond, it's like giving a handshake and give them a high five at the same time. Just to reach and give a high five, that means the 2 of us are going to have to come closer. Double bonds are always shorter than single bonds. And then if I want to give somebody a triple bond, that would be a handshake, a high five, and then I'd kind of like almost have to give them a hug. And by that point, the two of us are really close. Triple bonds are much shorter than double bonds or single bonds. Okay? So when we study ozone, if the molecule existed as a single bond and a double bond, then when we did chemical studies of these molecules, you would actually be able to tell the difference between the two bonds of ozone, the double bond to one oxygen and the single bond to the other. In reality, though, in studies, they've shown that the bonds between all the oxygen atoms are all equivalent to each other. The bond over here is equal length to the bond over here, which means the amount of bonding has to be consistent on both sides. Okay? Now, how much bonding is there? The bond order is a calculation we can do. Basically, I look at this and say, okay, but in this molecule, the center atom has 3 bonds going out, and it's a double bond and a single bond, but if there's 3 bonds being shared between 2 outer atoms, the bond order equals 3 bonds being shared by 2 atoms on the outside. 3 bonds over 2 atoms is going to be 1.5. That's a bond order of 1.5. It tells me like a bond order of 1 is a single bond. A bond order of 2 is a double bond. So a bond order of 1.5 is exactly halfway between. Okay, so that's a calculation we can do. The bond order right here, the BO equals 1.5. All right, next thing we can show, what about charges? If I look at my 2 structures, the middle oxygen has a positive charge here, and it has a positive charge here. So if it has a positive charge in both places, that means it always has a positive charge. Then I can put it there on the resonance form, the average, say that oxygen always has a positive charge. But then let's look at the oxygen on the left. Up here in this structure, it doesn't have a charge at all. But in this structure, it has a -1. So basically, it has a charge half the time. What's half of a -1 charge? The charge on this oxygen is -1/2. Then I look at the other oxygen and say, well, in this structure, it has a -1 charge. In this structure, it doesn't have a charge. So he also has a negative charge half the time. So his charge is -1/2. So what does that show us? Well, basically, no matter which structure we look at, the middle oxygen always has a positive charge, but the outer oxygens are actually sharing the charge. They're splitting it up. Half the time he has the charge on the right, the other half the time he has the charge on the left, but really the charge is evenly distributed between those two. So this is my best structure that I could draw for ozone. And actually I can show the lone pair on the center atom, because again, he always has a lone pair in both structures, lone pair, lone pair. Now the lone pair on the outer oxygens, sometimes they'll show them, sometimes they won't, because what happens is in one side it has 3 lone pairs, but then here it has 2. So whether I put 3 or 2 on that oxygen can get a little confusing. We usually don't get too picky about that. The things that we want to see, we wanted the dotted line to represent the partial bond. We want to show the charges, and specifically, if the charge is being split up between different atoms, we want to show the partial charges between them. Okay? Now, finally, if I ask questions on a test, how do you know what to draw? Okay? Well, let's boil it down. If I say draw the Lewis dot structure of ozone, you could just draw one of these structures. This one or that one, either one would be okay. If I just want to see the Lewis dot structure, just draw one of them. If I ask you to draw all resonance forms, that means in this case there are 2 distinct resonance forms. 2 structures that are similar to each other but not the same. So those are the resonance forms of ozone. And then finally, if I said draw the average resonance form, that's this one down here, where it shows the partial bonds and the distribution of charges around the molecule. Okay, So that's it for now. In the next video, we'll do another one of those just for practice.